Okay, now let's make a transition to full projectile motion.
Presenting
It's metal on board angles.
Medieval Knievel.
So what angle maximizes the range?
Thank you. Thank you very much.
You're brilliant.
Please. Not everything can be as good as the original, but Diet Dr. Pepper is.
Obviously, it's not the right angle. So what angle maximizes the range? Okay, guys, let me ask you a completely different question. What angle maximizes the range? Oh, okay, I see 45 degrees. How do you know? How do you know that the 45 degrees maximize the range? All right, so those of you guys who say 45 degrees maximize the range, how do you know that? All right, you know that because most of you guys, for most of you guys, it's book knowledge. I don't really rely on book knowledge that much because this is something that you can learn through experiment. I knew that when I was a kid. The reason why I knew when I was a kid is because I grew up in Turkey, and I know baseball is huge in the United States. Don't care much for baseball. I find it really boring. And maybe part of the reason is because I don't understand the game. And so I grew up playing soccer, and when I was growing up, we didn't have a lot of parental supervision, so it was fun. So you would play for hours and then drink water. And then in order to make it competitive, we used to do pissing contests. That's a real thing. All right, so for trial and error, you discover that, hey, 45 degrees is going to maximize the range. So you don't have to look it up. You can actually experiment. For odd thing is, though, forget 45 degrees. It's going to maximize the range. But look at 75 degrees. Look at height you can gain at 75 degrees. Stuff that you can do with it at 75 degrees. So imagine that you're at a baseball park, been there a couple of times, all right? The game is boring enough, so most people drink, including myself. So if you're drinking, obviously you gotta go piss, and then when you go to the bathroom, there are lines. So what I'm about to say is gonna make perfect sense to you if you're tipsy and drunk. Okay, you're in a hurry, you have to go, except you cannot hold it much longer. And you're right behind this guy, and you're thinking to yourself, I wonder if I could piss over this guy's head. And you know, it might be possible at 75 degrees, all right? All right, so if you want to try something like this, my recommendation is practice. This is something that you have to practice at home. All right, get your little sister or brother, check to see if you can piss over somebody's head. The last thing you want to do is try to piss over somebody's head while you're tipsy in a park. All right, because you're going to end up hitting someone in the back of the head, and nothing is going to piss someone off more than getting pissed upon. All right, so remember, 75 degrees is the way to go, and 45 degrees is going to maximize the range. Another thing that I want you to know, when you guys are solving problems, when somebody says 45 degrees in a problem, they will never, ever, ever give you the angle. All right, it's assumed that you know that it's going to be 45 degrees. All right, so got the best answer. I put it in the chat. Okay, this was fast. All right, so it's 45 degrees.
Radar sees precipitation. It sees thunderstorms. Radar does not see clear air turbulence, and that's the difference.
Severe clear air turbulence is very rare. That's what the planetones and converses experienced. It strikes most often above mountain peaks where the winds flow like waves. Small clouds called rotors form within the motion and then quickly disappear, leaving a vicious rotating air mass. While computer models attempt to forecast clear air turbulence, pilots usually fly into it blindly. Sometimes it even occurs above flatlands or over water.
Good morning, ladies and gentlemen. Welcome aboard United Airlines Flight 1586.
Just ask United flight attendant Lisa Stream. In 1992, she was preparing the cabin for landing as the Jumbo 747 began its descent into Miami. Out of the blue, the plane suddenly dropped, and Lisa was tossed straight up.
I slid along the ceiling, and when we started to bottom out and I started falling back down to the floor, our passenger took my ankles, and he pulled me down, and we hit hard, and I kind of landed on the armrest. That's when the cart actually landed on the top of my foot.
Flight attendants are especially at risk. Lisa's injury required surgery. Doctors amputated a toe, and she was unable to fly for 2 years. Why do people and things become projectiles when a plane hits rough air? Captain Vanderberg explains it's the laws of physics.
The plane itself is still flying. It's not falling. It's flying perfectly well. The trouble is the environment it's flying in now is all going that way. And so as it heads down in that downdraft, as you might imagine, that will reduce the gravity possibly beyond zero, which would cause objects and people that are not securely strapped down to rise out of there.
I think everyone should wear their seatbelts all the time, especially kids. I think kids should be in car seats. Even a mother's love can't hold that baby safe. It takes a child seat to do that.
That's the government's message, too. A message the planetones have taken to heart.
Keep your seatbelt on at all times.
I can see. Cool. All right, so air turbulence. All right, so basically here's the airplane. Unbuckled passengers inside. Airplane flies into air turbulence, so passengers will get slammed against the ceiling. This is the guy on the 10th floor. You'll see the open neck, right? All right, so you come up with a theory. So the theories are usually come up by theoretical physicists, and they usually express it in the form of mathematics. So it has to be peer reviewed. So the theory that most of you guys came up with is this. All right, so like 90% of you guys came up with this, believe it or not. So the guy inside the elevator cable snaps. His tongue is sticking out. He goes up, hits the ceiling, what goes up, first the second impact is going to break his neck. All right, so once you have a theory like that, the experimentalist wants to do the experiment. So one way of doing it is bring a bunch of you guys inside the elevator, snapping the cable, which you cannot do because it's illegal, or you have to do an thermal experiment. All right. When I do the experiment, just follow. We got this ball, so just follow the ball. When I'm going to drop it, what should happen according to your theory, and there's a distinct prediction. As far as you guys are concerned, this ball is going to go to the top, right? How many of you guys still think that if I do this experiment, I'm going to drop it from here and catch it here, guys. This is like 0.3 of a second. Okay, how many of you guys think that this ball is going to rise to the ceiling? Anybody?
No.
Okay, I'm looking at your responses. You guys, I mean, we've been doing this stuff for about a month. All of a sudden you go, wow, that doesn't make sense. Immediately, you guys are far better today than about a month ago, because most of you guys thought this ball was going to rise to the ceiling. No, it's not going to happen. Some of you guys are thinking, yeah, but because the distance is too short. Yeah, if that's the case, I'm going to go to an expert, man. I'm going to give you a theory that I got from a theoretical physicist. And I know I can trust this guy because he has a PhD in quantum gravitational field theory. He said, Karen, he said the ball shouldn't, obviously it's not going to rise to the top. Instead, he said the ball is going to rise to the middle. It's just going to go to the middle right here. Got it? The reason, he said, because the center of gravity of the elevator is located right in the middle. So the center of gravity is located right here. So the ball is in free fall. It's going to go get sucked to the middle. It's going to become suspended right there. Do you see it? The ball is going to be right there. So I'll do the experiment for 0.1 of a second. Just watch it carefully. I want you to verify that the ball goes to the middle and becomes suspended. Can you do that? You don't have a choice. All right. So don't blink, because if you do, you will miss the entire thing. Okay. Ready? All right. Watch it carefully. Did you guys see the ball rise up? Yes or no? Okay. Watch it again. Did you see the ball rise up? Yes or no? Did you see the ball rise up? Yes or no? What the hell is wrong with you guys? The answer should be yes. Let's do it again. Look, guys, this guy has a PhD in physics. You guys don't, so it can't be wrong. Okay, so let's do it again. Did you see the ball rise up? Yes or no? Now you guys are changing your minds. It's called social pressure. Did you guys see the ball rise up? Yes or no? Most of you guys should say no. Now your answers are kind of in the middle. You can't really see. Number one, it's happening too fast. Number two, you get tons of reflection, and you can't tell. It doesn't seem like it's rising up. It may be gravity today, guys. It kind of sucks. Maybe we should just do it here. Did you guys see it rise up? You can't really tell because the things are happening way too fast. So let's test it a little bit different. Right? Okay, so if the keys rise up to the middle, this is what you will hear, right? Got it? You hear it clearly. All right, so when I do the experiment, if this guy is right, if this physicist is right, you will hear this. All right, when I catch it right here, you will hear this. Okay, so I'm doing the experiment. You're not going to be able to see anything, but listen for it. Did you guys hear anything? Okay, no, the keys don't leave the floor. Okay, Liz said everything is going to follow the same rate of acceleration. A vacuum in an airless environment like the surface of the moon. Remember this little thing? Remember this little thing? Remember this? Drop from the same height. Everything falls at the same rate. So let's say, wait a minute. Yeah, but it's in a vacuum. Watch this. Watch this. Whoa, 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 whoa. They don't fall at the same rate. Oh, damn. This life is so confusing. I don't understand. When you do physics, you want to kill yourself. It's just so aggravating. Keys fall faster too. But now look what happens when I shield everything from the effects of air friction. This is not a magic trick, but I'm going to make it look like it's a magic trick. All right, when you drop and watch the piece of paper, everything still falls at the same rate, right? So shielded from the effects of air friction, paper, the keys, everything falls at the same rate. Now remember, elevator is relatively heavy in real life. Distance fallen is relatively short.
So the effects of air friction don't matter. So the elevator, the person, everything inside will fall at the same rate.
No chance whatsoever. We're not even done. This guy's a broken neck. He's got a broken neck, despite the safety system. Safety system, when it kicks in, it brings you to a stop very gently. I don't know if you guys have Six Flags in Houston. We do here. All right, so there's a giant drop. You get in there. All right, so they put you in a following elevator, and guess what? Everybody's fine. I wonder why. I know the reason why, because of the safety system. This guy's a broken neck. So all of a sudden, it gets more confusing. How did he break his neck? This scenario even remotely possible. Is it something that I end up pulling out of my butt in order to make it interesting? I got news for you. I made it out. Knowing full well that it might happen one day. If I'm lucky enough, I would probably catch it in the news. And that day came and passed.
Elevator plunged 40 stories. That story topped tonight's news briefs. Miraculously, the woman suffered only minor injuries. One woman broke her ankle, the other broke her leg. After traveling down 6 floors, the elevator suddenly broke loose and began its free fall descent.
So you got 2 people inside the elevator. Cable snaps, free fall. They got broken legs. So it is possible to break a leg, break an arm, break your back. So everything is possible despite the safety system. So the question is how. So we'll keep investigating. The only thing I want you to know is projectile motion, right? Projectile motion is the same as free fall. Notice that it falls. Okay, imagine the airplane just flying in the horizontal direction. Turn it sideways. So imagine that the airplane is moving in the horizontal direction. So this is free fall. Everything is falling at the same rate. Now here's the airplane flying horizontally this way. It's falling under the influence of gravity. So everything is still going to fall at the same rate, right? So no one is going to hit the ceiling. No one should be hitting the ceiling. Yet they report people hitting the ceiling. How's that possible? Is it possible for you to hit the ceiling? If gravity is the only force acting, if the gravity is the only force, only reason why things are falling, no one is going to hit the ceiling. But what if it's being pushed down? Notice that now I'm pushing it down. When I'm pushing it down, notice that the ball goes up, hits the ceiling. In fact, let me make it more obvious. Notice that the keys go up and they hit the ceiling. So what's happening is, airplane is going through a projectile motion, but it's not falling under the influence of gravity. It's actually falling under the influence of forces generated within air turbulence. And the acceleration of the airplane is larger than the acceleration of the people on the inside. People on the inside are shielded from the effects of I was going to say air friction. They're shielded from the effects of air turbulence in a sense. The airplane is the one which is being pushed down, not the people, obviously. So people are falling under the influence of gravity, so they're undergoing free fall. The airplane is falling at an acceleration larger than the acceleration of the people on the inside. Okay, so if you're not wearing a seatbelt under the circumstances, yes, you will get slammed against the ceiling. And the reason why this happens is something we will discuss later on. All right, so the airplane becomes part of the air mass that is flying in. If the air mass goes up, it's going to take the airplane with it. If it goes down, once again, it's going to take the airplane with it. The problem happens when the air mass starts to go down at an acceleration larger than the gravitational acceleration. So, which means that the people inside, if they're not buckled down, they're going to get slammed against the ceiling. Okay, so I love this picture because these pilots turn the airplane upside down. They're accelerating towards the Earth at an acceleration larger than the acceleration due to gravity.